Now it is time to put together all of the pieces for our first real inferential test. We're going to learn how to use a one-sample z-test for hypothesis testing. Now, one-sample z-test is a parametric procedure. That means that it is using data from the population. So, a z-test will tell us whether a sample mean differs significantly from the population mean when the standard deviation of the population, or sigma, is known. Now, you may remember the example that we did with polar bears, and we were interested as to whether caffeine would cause the polar bears to wander farther in a day than simply wandering around without caffeine. We found that the average distance that a polar bear would travel in a day is 100 kilometers, and you didn't know this, but I looked it up and I found that the sigma, the standard deviation for this number, is 11. Now, actually, these numbers are made up for illustration, but we do need to have some kind of standard deviation for this all to work. Now, you remember that polar bears that drank caffeine, they wandered 150 kilometers in a day. That sample that started with a mean of 100 now has a mean of 150 as the result of drinking caffeine. So we would say that the mean of our sample is statistically significantly different than the mean of our population. Well, how exactly do we go about saying that? It's because we used a z-test. I'm going to show you a different example, give you some real numbers, and let's actually try this. So here's our example. With the increase in social networking usage, researchers are interested in the patterns of usage, especially in the age of users. So we find out that the average age of social media users is 36.9. And this is an example that I got from a website called Pingdom. So we have a sample, that's the smaller circle with the M and the SD. That is a sample drawn from the population. It has a mean and a standard deviation. The population also has a mean and standard deviation that are represented by mu and sigma. The population is all social networking users, but the sample is users of the site LinkedIn. And what we want to know is whether LinkedIn users are different than the average user of all social media. Are they older, younger, different in some way? That is what we're going to find out. So we put together our research question in this way. Researchers at the website Pingdom calculated the average age of users of social media websites and found that the average age of social network users in the United States is a mu of 36.9 with a standard deviation of 10. This distribution is approximately normal. You sample 25 users of the social media site LinkedIn. The average age for your sample was 44.2 years old. So we know that on the average they're older, but is 44.2 statistically significantly different than 36.9? Is the average age of your sample of LinkedIn users different from the U.S. population of social network users? That is what we're going to test. So our research question becomes, is the average age of the sample of LinkedIn users different from the U.S. population of social network users? Well, are we going to use a directional or non-directional hypothesis? We're asking whether LinkedIn users are different. Are we asking whether they're older? Are we asking if they're younger? We're only asking if they are different. So is that directional or non-directional? That is a non-directional hypothesis, so we will use a two-tailed test. We have a mean of 36.9, a standard deviation of 10, a sample size of 25, and a sample mean of 44.2. Those numbers will stay on the screen at each stage, so you'll be able to refer back to them. You'll know where those numbers come from. We will need all four of those numbers. All right, let's get started doing our 5 steps of hypothesis testing. So, if you want to refer to the handout that I've given you about hypothesis testing, you'll find this example, the 5 steps. Let's work through these 5 steps using a z-test. Remember, we're going to use these same 5 steps for every new test that we learn. Step number 1, choose the appropriate statistic. And I told you this would be the easiest of the 5 steps because the appropriate statistic is whatever test we're learning this week. And so what would be the appropriate statistic for this research question? We will be using a one-sample z-test. So that was easy enough. Let's move on to step 2. In step 2, we have to outline our hypotheses. Our null hypothesis will be that the sample is no different than the population. How would you put that into words? LinkedIn user's age is no different than the average user. How would you put that into symbols? H sub 0 mu equals 36.9. Or said a little differently, the sample is drawn from a population that has a mean of 36.9. Now we have alternative hypotheses that could be one-tail or two-tail. We know that we're going to use a two-tailed test, but let's also practice with a one-tailed test so that we're getting a little more practice with understanding how to create hypotheses. So let's start with our alternative hypothesis for a two-tailed test. We're saying that LinkedIn users are different, but we're not establishing a direction. So in words, LinkedIn users' age is different than the average user. And in symbols, our H sub 1 would be mu does not equal 36.9. The sample of LinkedIn users is drawn from a population that does not have a mean of 36.9. But let's practice one more time. How would we create a one-tailed hypothesis? So we suspect that LinkedIn users are older than the average user. That would be a greater than symbol. So in words, LinkedIn users are older than the average user. And in symbols, this is H sub 2, mu is greater than 36.9. The sample is drawn from a population, or represents a population, that has a mean greater than, or older than, 36.9. Now that we have our hypothesis, our null and our alternative hypothesis, we are ready to move on to step number 3. How many tails are in this test? How many tails are we using? Remember, we assume it is a two-tailed test. We know that because we're just looking for differences, not older or younger. What is the alpha level that we'll be using? 0.05. What is the critical value? For a normal distribution with an alpha level of 0.05, what is the z-score that we must exceed to have fewer than 5% of the scores in those two tails? This is one that I'll give to you. It's simple for a z-test, but as we learn new tests, we'll find we have to look up this critical value in a table each new time. The answer for the critical value is a positive or negative 1.96. So if we calculate a z-score that is greater than 1.96 or less than negative 1.96, we will know that our sample is statistically significantly different than our population. So let's calculate the statistic. Here's the formula. M is the sample mean minus mu, which is the population mean. Sigma is the population standard deviation, and n is the sample size. Notice that the standard error of the mean, or sigma, divided by the square root of n, is what is being used in the denominator for the z-test. So let's apply this. Remember that all of the numbers we will need are included at the top of the screen, so if you ever get confused about where a number is coming from, refer back to those values. We're going to calculate first the standard error of the mean, which is the standard deviation, or sigma, divided by the square root of the sample size, or 10 divided by 25. Square root of 25. So the square root of 25 is 5. 10 divided by 5 is 2.0. So 2.0 is what is going to plug in to the denominator of our z-test. In the numerator, our z-test is the sample mean, 44.2, minus the population mean, 36.9, divided by the standard error of the mean, which we've already calculated as a 2.0. That's a 7.3 divided by 2, which is 3.65. That is our z-score. We have calculated a z of positive 3.65. We're going to compare that to our critical value of 1.96. Does 3.65 exceed 1.96? Yes, it does. 3.65 is larger than 1.96. It is further away from the mean. Remember, the mean is 0 in a z distribution. So this z of 3.65 is farther away from the mean than our critical value of 1.96. Let's look at that in a picture. So here we have our distribution. We have our two cutoff scores at positive and negative 1.96. Those are the two fences. And we have that purple shaded area, which is our region of rejection or our critical region. It's the area where if the value we calculate falls into that area, we will reject the null hypothesis. So as we look on the x-axis, we see a mean of 36.9 is right in the middle of that bell curve. But follow out to the right, find 44.2, see how it is over the fence. It is in that purple region of rejection. It is in the critical region. So the observed value of z equals positive 3.65 exceeds the right critical value of z equals positive 1.96. That's the fence. Therefore, the difference is statistically significant at a p-value of 0.05. So the probability of getting a 44.2 if that sample is really part of a population that is a mean of 36.9, less than 5% of the time would that outcome occur by chance. So the probability is less than 0.05. Remember that the fence represents an alpha equal to 0.05. Scores inside the body of the curve are greater. The probabilities are more likely. There's a lot greater likelihood that we'll get scores close to the mean. But outside of the fence, that purple line is getting closer and closer to the x-axis. Probabilities are continuing to drop. Sample means falling far from the population mean are highly unlikely. They're far out in the tail. Now that we know the results, it's time to write them up. In your homework, you will see these steps, and these are the things you should be including in each of these steps. And I'll give you a hint. Always include all of these details. So number 1, the appropriate statistic is a one-sample z-test. I've put in parentheses that we're comparing a sample and population. You don't have to include that on your homework, but it is there to just help you remember what we're doing with this test. State the null and alternative hypotheses. For these, you should use the symbols, not the words. So you would have h sub 0 colon, mu equals 36.9. That's your null hypothesis. Your alternative is h sub 1 colon, mu does not equal 36.9. The level of significance. We're using a two-tailed test. Alpha equals 0.05. Be sure to include two-tailed test. Don't just write a 2. Don't say two-tail. It's a two-tailed test, comma, alpha equals 0.05, which gives us a critical value of 1.96, or more accurately, positive negative 1.96, because we are using a two-tailed test. Though the statistic that we calculated was a z of positive 3.65, which we know exceeds our critical value of 1.96, and so we conclude that the average age of LinkedIn users is higher than the U.S. population of social networking users, comma, z equals positive 3.65, comma, p, or probability, less than 0.05, period. And now let's write up those results in APA style.